Hello, welcome to Econometrics Melody. In this video, we will discuss about the expectation of the random variable. In our previous video, we have seen about the different types of random variable, discrete random variable, and continuous random variable. And let us begin with their review or summary. So the discrete random variable, they are going to take the countable numbers as their values like 0, 1, 2, 3, 4, and continuous random variable, it also accepts the decimal points, meaning thereby it takes the real numbers is their value. Interval, it is continuous random variable is defined for the interval. And when we plot the frequency or the probability against the random variable, then we get the bar graph in case of discrete random variable, or this spike kind of graph, and we call it by the name probability mass function. And the same for the continuous random variable, we get the continuous graph is shown in this figure, and the area enclosed by that graph is equals to 1. That should be equal to 1. Similarly, for the discrete random variable, if we add all of this probability, individual probability, that should be equal to 1. And the probability density function, it is generally represented by or denoted by the function f, x, small f, and x. The cumulative distributive function is denoted by capital F and x. And for the discrete variable, it begins with the minimum value and it stares up and it reaches the maximum value. And we get the cumulative distributive function by adding progressively the probability mass function for the discrete random variable. And for the continuous random variable, the graph of the cumulative distributive function is something like this, it like the later years, and it depends on the kind of the distribution. The CDF is denoted by capital A of x. And in case of the continuous random variable, we integrate the probability density function in order to get the cumulative distributive function represented by this relationship. And it's already mentioned, the continuous random variable, it is defined within an interval for an interval. So the cumulative distributive function for this interval AB is given when we integrate it from A to B, and this fx, it is the probability density function. And this is equal to the cumulative function of the highest minus the cumulative function for the lowest. So for the discrete random variable, if we want to calculate the CDF for, that is the probability of x is less than equal to, let us say, 5, then we add the individual probability from the minimum all the way to 5. And same applies to this continuous random variable. If you want to calculate the probability of x is less than, let us say, 1, then we integrate it from this minimum 0 to 1, or whatever minimum value to that desired point 1. And in discrete random variable, we can calculate the probability for the particular point. Let us say the probability of getting 1 over here, this is equal to this value. And in case of the continuous random variable, we define the probability for a certain interval. So for the probability for certain point, that is 0, which can be clearly understood by this relationship. Let us say if we want to calculate the probability from point A to A, then this value fa minus fa, that would be equal to 0. So we cannot calculate the probability for a point in continuous random variable, it is 0. But for a certain range, the probability, let's say, is, for example, the probability between 2 to 3, that is equal to the cumulative distribution 3 minus the cumulative distribution of 2.2. While for the discrete random variable, we can calculate the probability for certain particular point, and for the interval, let us say this example, the probability for between 2 to 3, that is equal to the probability of 2. That is why we notice this stair, ascending stair. Similarly, the probability between 5 and 6, we take it as the probability of 5. And in the continuous random variable, if we know the cumulative distributive function, we take the derivative of it and to calculate the probability density function. And if we integrate the probability density function, then we get the cumulative distribution function. Now, after this quick review, now let us proceed to today's topic, and it is expectation of a random variable. And I have made this template ready. I have drawn it from the previous example of rolling 2 dice, and our random variable x, it records the sum of the numbers that appears when rolling 2 dice, so all the possible sums. And we have its frequency, and to be more precise, we have its probability. And now we have our random variable x, it is ready, and also we know its probability. So if we know the observations contained by this x, variable x, and we know, if we know its probability, then we can calculate its mean, variance, and if there are a number of such random variables along with its probability, then we can calculate their covariance and their correlation and so on. And let us multiply the value of x with the probability. For this particular observation, it is 2 by 36, and 2 it is 2 by 3 to the 6 by 36, and so on. We can calculate their product and we can sum them. So let us focus on notation only. So we can sum the product of the respective observation x along with its probability. Let me call it as xi and pi. So where I is equal to, it begins from 1 to n, and n is equals to 11. And also we have this feature, when we sum all the probabilities from I is equals to 1 to n, that should be equal to 1. So therefore the expectation of a random variable x, let me write it as capital X, this is equal to summation of, we take the product of the probability and that observation, and we sum it from the observation of 1 to n. So this is true for the discrete random variable. And what will be its continuous random variable counterpart? Let us see that as well. Therefore let us write it, expectation of x is x. For the summation, we integrate it, let us say, from minus infinity to infinity. The lower and upper bound, we take it is the domain and the interval in which this function is defined, and we take it as fx. This is our probability density function. Then after we multiply it with by the x, so we are done with this. Integration is equivalent to summation, and this fx is equivalent to this probability, and then x, we have x over here, and we take the integration of it with respect to x. So this gives us the mean or the expectation of the random variable x when the random variable x is the continuous random variable. Now let us see some of the conditions. If we take the cube of the random variable x, how do we calculate the expectation of x cube? So it is very simple. In this case, expectation of x cube is given by the summation. We follow the same principle. So we take the product of the probability and the cube of that particular observation, and we take the sum of this from I is equals to 1 to n. And this gives us the expectation of variable x cube, where x is our random variable. So this is the case of discrete random variable. And if x was our continuous random variable, then the same, we would calculate it by using x and then fx. So using this formula, it is very simple, because expectation of x is equals to this integration x fx dx. And let us see another important point. So from this reference, we can say that the expectation of the function of random variable x, this is equal to the summation of I is equals to 1 to n, and that we take the product of that function of x with the probability, and then we sum it from 1 to n. So this should give us the expectation of the function of x. So when this is our discrete random variable, so drv, and the same when x is our continuous random variable, so we integrate it from its lower bound to upper bound, or the interval on which this function is defined, or the domain, and we take that function of x, and we take the product of the function of x along with the probability density function dx. And another property, let us say the sum of the, so the expectation of the sum of the random variables. So let us say x, y, and z, they are the random variable, and we sum them and we calculate the expectation. So this is equal to the sum of their individual expectation, and this is true for both the discrete random variable as well as the continuous random variable. Let's say we multiply our random variable x by certain scalar a, and then to this product we add certain scalar b. Scalar here means some constant. So this is equivalent to scaling our random variable and plus b. So addition or subtraction, this means to shifting their origin. So, and we define this is equal to our random variable y. So how do we calculate the expectation of y? Expectation of y, this is equal to a random variable x plus b, and we can operate their expectation individually. So e a x and then plus expectation of b. So age a is our constant or scalar, it comes outside of the expectation, it is this plus an expectation of the constant is, for example, so we have a probability 0.4 and 0.6, and if our this b is constant 4 and 4, so irrespective of the probability, our expectation of b, that is, let me write it as bi and bi, so if we sum it, this should be equal to b, and we get b. So if we compare it in this way, we had y following this rule, and our expectation of y also follows the same rule. When we construct a variable y by scaling the random variable x by some unit and shifting its origin by b unit, then we attain the expectation of y by scaling the expectation of x by a unit and shifting the origin by b unit. So the expectation of y also retains the same feature in terms of the scale and shift in the origin when compared with the property of its construction. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.